Welcome back to ECE 2002. After having a little bit of discussion with the students, I wanted to give people a brief update. Exam 1 grades are not quite yet ready to come out. I'm missing like 4 of them, and since I'm grading on a curve, I can't really release anyone's grade until I have everyone's grade. So, I have all the formulas set up. The standard deviation has widened a bit. Like yesterday it was like 15.2. Now it's like 20.5. So apparently all the outliers were in one part of the alphabet. Not all the outliers, but a little bit more disparate scores were in one part of the alphabet. That means unless you did like really, really, really well, everyone is basically within 2 standard deviations of the mean. So everyone's getting a grade between 60 and 100 for the most part. So like, because the standard deviation is so wide, I don't think anyone's actually going to fail. Like, very few people are going to fail, I should say. If you didn't hand in anything, I can't do anything for you. You get a 0. No, the curve is more generous the lower your score is, just because of how the mean shift works. And by curve, you mean like the points added on? Yeah, that's what I meant. So you get more points added the lower your score was. So, like, if you scored below a raw 40, maybe you need to rethink how you completely do this exam. But if you scored above a 40, unfortunately, like you're probably in really good shape for this class. It's all relative. Homework 3 grading has started, so I'll hopefully get that out by the end of this week. But I'm starting to learn that I can't make promises when it comes to grading. Homework 4 is due tonight. Make sure you get that done. We will have quiz 4 this weekend, so be prepared for that. Pay attention to everything we've said so far with Laplace transforms and with what we're talking today about frequency response. What else? I did upload one thing by request. I got this done as well. But if I share my screen, you can now see I added to the exam 2 and final exam section the tables you will get on those 2 exams. You'll get the same tables. So you'll get convolution properties. So, definition of convolution, the shifting property, time shifting property, all of these other properties we talked about in the lecture. Okay, Phil. Integration, differentiation and convolution, and general differentiation and integration properties. So yeah, feel free to use this on your homework to get prepared. Butterworth polynomials is not something we'll deal with until lecture set 7, so I'll just ignore them for now. Then on the back page, this will be the very last page of your exam. You'll see your Laplace transform properties and Laplace transform pairs. So, you'll see the definition of the Laplace transform, linearity, time derivatives, higher time derivatives, frequency derivatives, higher frequency derivatives, something that I had an error in the lecture set, I just realized. Time delay, frequency shift, time integral, frequency integral, which is one we didn't talk about, time and frequency scaling, which we didn't talk about, complex conjugation we didn't talk about, convolution and multiplication properties. So you should have more than enough properties to solve any problem you need with Laplace transform. And then we have Laplace transform pairs. So I was fairly generous in which ones I included. So unit impulse, delayed impulse, unit step, delayed step, ramp function, nth power times a unit step. The rest are all times a unit step. Exponential, cosine, sine, hyperbolic cosine, hyperbolic sine, which you shouldn't use because they would be unstable. Exponential times an nth power, exponential times cosine, exponential times sine, cosine times ramp, sine times ramp. Which the last ones are very hard to get by inverse Laplace transform, I found out. So there you go. I will be in person office hours today because I'm getting my workstation back. So I will be in person. If you ever are uncertain if you want me to be in office hours, or if you're ever uncertain if I will be there, just send me a message and I will make every effort to meet you or make an appointment with you. I will do, I am available by appointment for office hours if you can't make my normal times. Will exam 2 be like the homework exam? Yeah. Boyu, I think, has done a really good job helping me with the questions. He was the mastermind behind the questions of exam 1. Don't take it out on him. Still was still my choice at the end of the day. But hopefully you found that the question difficulty wasn't bad. It was just the length of the calculations involved. I think that's the consensus is, every question asked was pretty fair. It's just, there wasn't, the amount of work to do for the time allotted was too much. Okay. But, I recommend for your, homework and stuff like that, you start getting used to this Laplace transform table because it's the one on your exam. Let me know if you see any issues with it, whether it's hard to read or it's, missing something you think it needs, or it's, has an error in it, which I don't think it has any errors in it, but, if you find an error, do let me know so I can fix it for everyone. I think I did a good job on it, but that's me. I always like my equation sheets. Give you everything, let you hunt for it. That's my philosophy with equation sheets. Any questions about Laplace transforms or homework 4 before we begin frequency response? You will have the same. You'll have the same list of tables that I just showed, so on. However, your equation sheet will be a little bit longer. I'm thinking I can fit everything onto 2 pages front and back in terms of just pure equations. You're welcome. Yeah, because I gave you the Butterworth polynomials, but you won't need that for exam 2. You'll need that for the final exam. Preview of what's to come. Obviously, we've talked about convolution and Laplace transforms to the extent we're going to. Any other questions? Hopefully everyone's good. I want to see, nice, nice high scores on homework 4 when we get around to grading it. All right. I'm still sharing my screen. Let's talk about frequency response. So I'm always excited when we start a new lecture set. So here's lecture set 5. You should be able to find it on Brightspace if you haven't downloaded it yet. So you can take your own notes on it. But we're covering, the textbook chapters 25 through 29. So I consider this to be, kind of 1 unit of information, though there's a little bit of stretch of ideas in here. So first of all, we'll talk about the complex plane instability. So this is where we're going to do, some, math, understanding complex numbers a little bit better, get some definitions out of the way as well. And then we're going to talk about resonance and second order systems, which is just a little bit of an exploration. We're going to, revisit second order circuits, so the LC and RLC circuits, and see what exactly we get. Then we're going to get into frequency response itself. So this will be the heart of the lecture set, where you talk about how you do it algebraically, graphically, and then we'll do an approximate graphical method called the Bode plot. And unlike most graphical methods we talk about, being able to do a Bode plot will be considered, very important. And then we'll get into magnitude and frequency scaling, which is a good engineering skill to have. So it tells us how we go from the very nice numbers we were dealing with, where we deal with, 2 ohm resistors, 2/13 Henry farads, and maybe like 5 farad capacitors. And how do we scale them down to values you can actually buy and use and find in a store? And then lastly, we'll talk about bandpass response in second order systems. So it's kind of a revisit of the resonance topic, very highly related to it. And we'll talk about the parallel and series RLC circuits about how you get what's called a bandpass response, which will serve as a good segue into filters in the next 2 lecture sets. So why study the poles and zeros? So the frequency response of a circuit, which is how both the magnitude and the phase of an input sinusoid will change to become the output sinusoid, is one of the most sought pieces of information relating to the circuit. AC is everywhere in the world, so we're exciting things with sinusoids. You learned in ECE 20001 that all you need to keep track of for a linear circuit, because it has the same frequency, is how the amplitude changes, hence the magnitude, and the phase changes, the angle in the sinusoid. And, because, we use AC to represent that, you can break down signals by a Fourier series and get, sums of sinusoids. You basically learn, sinusoids are everywhere, even where you least expect it. So you want to understand how the circuit responds to, a sinusoid of a given frequency, and how the magnitude and phase will change. And the frequency response is so important that you basically have a whole second course about it in ECE 301. Frequency responses, taking up, a bulk of, ECE 301 topics too. So we're just going to get a taste of it, which will be good, look at the material. It's fairly thorough. And then in ECE 301, you're going to, really dive deep into it and explore the nooks and crannies of the topic. Or I guess the subject, I should say. So it's worth understanding the structure of a generic transfer function to see how it affects the input response. So, we talked about this transfer function view of things, where we don't need to care about the circuit topology. We can just, look at it mathematically and understand it. So we're going to, not look at circuits right now, look at transfer functions and see how it affects the input response. Because we deal with transfer functions that are rational functions, again, they have a polynomial in the numerator, polynomial in the denominator. We'll look at the roots of the polynomial in the denominator, which are called the poles, and the roots of the polynomial in the numerator, which are called the zeros, separately, and see how it affects the behavior of the output for a given input. And specifically, we want to look at, a sinusoidal input with a sinusoidal output. So, just the button too many times. So we'll have a transfer function h of s, and it's going to be written as the ratio of a polynomial of degree m to 1 of degree m, where m is less than or equal to n. But, we'll write it as a sub m times s to the m plus a sub m minus 1 times s to the m minus 1 plus all the way down to a sub 1 times s plus a naught. All over s to the n, where we don't have a coefficient, in front of it, because we can always, rewrite the rational function to remove one coefficient. So we'll have s to the n plus b sub n minus 1 times s to the n minus 1 plus all the way down to b sub 1 times s plus b naught. So, you can divide out, the leading term k. So you will call it k. And then we'll have a factored polynomial in the numerator. Remember, we can always factor the numerator by the fundamental theorem of algebra. There's always going to be m total zeros, as we'll call them. And in the denominator, there's going to be n total poles, but, we have to deal with multiplicity. So we'll have the transfer function is k times quantity s minus z1 to the q sub 1 power. And then we'll have quantity s minus z2, quantity to the q sub 2 power, and so on until we reach, some, m z sub, something that's less than or equal to m. And, these multiplicity, we call these the multiplicity Q. Your book also calls it order, but we talk about the, order of a circuit, and I call it multiplicity because, that's a little bit less confusing. Doesn't have a terminology collision. The denominator has factors that are very similar to the numerator, except we swap them out for p's to stand for poles, and we call them multiplicities r. So we'll have s minus p sub 1 quantity to the r sub 1, and quantity s minus p sub 2 quantity to the r sub 2 power, and then so on until we have n total of those, or less than n. And we can write that as k, times, k equals 0 to the m product s minus z sub k to the q sub k. And we'll have over product from L equals 0 to N of quantity S minus P sub L to the R sub L. So basically, this was a lot of math and words to explain that, yeah, you can factor the numerator and denominator separately. You'll just get a factor of K out front. So what's the interpretation of zeros? Zeros are locations where the absolute value, the magnitude of h of z sub k is equal to 0. It's even true not in magnitude 2. If you plug in any of these, numerator becomes 0. 0 divided by some non-zero thing is going to give you 0. And the poles are where the magnitude of h of p to the L goes off to infinity. And either z sub k or p sub L can be complex. And notice we have to say the magnitude goes off to infinity because if you just evaluate h of p sub L, it can go off to positive infinity or negative infinity. They are the singularities or the poles, or what other term, the infinity points of this transfer function. Mathematicians have a lot of names for them. We'll call them poles. I guess the point, if you think about like a big circus tent or something like that, and you think about like the canvas that the tent is made out of, the zeros are the place where the tent will touch the ground, and the poles are the place where, if they were infinitely long, the poles would, be where the canvas goes off to infinity, or, so it, starts shooting off towards infinity. So I guess I'll write down the circus tent analogy. What questions do we have? Yes, the frequency response is fun. Though that probably wasn't said in response to the frequency response. Okay. I won't say you'll get extra credit, but someone on their homework drew this like fancy, drew out homework and with a very fancy like monograph H, but the H was made out of circuit elements. So like if you have good art to put on your homework, like it'll at least make me smile. I forget who even did that, but someone had a very nice, monograph H made out of circuit elements on their homework, and I thought it was good. But I can't give you any extra credit. So let's look at an example of poles and zeros. So say we have h of s is equal to 5, and then in the numerator, quantity s plus 3 times quantity s plus 7, all over quantity s plus 2 quantity squared, quantity s plus j6 times quantity s minus j6. Together, you could write these terms as, s squared plus 36. And then we'll have s plus 4 plus j3 times s plus 4 minus j3, where, if you were careful with your, distributive property, you could figure out what that would be in terms of like s squared plus something times s plus something. But I'm not able to do that real fast, where the something plus something, but all might be complex. Anyway, let's look at things very carefully. So we have a constant multiplier of 5 that doesn't affect zeros or poles at all. So the zeros are going to be at s equals minus 3, because this is a nice factored form. We can easily see we plug in minus 3, and the numerator will become 0. And then the numerator also becomes 0 if we plug in s equals minus 7. Both of multiplicity 1, or the other way of saying it is both are zeros of order 1. And the poles are the places where the denominator equals 0. And in this nice factored form, it's super easy to figure it out. So we'll get s equals minus 2 as a pole of multiplicity 2. And then we'll have s plus j6 and s equals minus j6. Well, this one is the minus j6 one. This is the plus j6 one. Those are each of multiplicity 1. And then we'll have s equals minus 4 minus j3. And then we'll have s equals minus 4 plus j3 being poles of each with multiplicity 1. So hopefully this isn't too bad. You're pretty comfortable working with this from previous exposure in algebra. Maybe it's your first time dealing with the complex numbers in it, but those can be factored too. So let's look at a pole zero diagram. So this is a brand new type of diagram. So far we've mostly been focused on plotting, we've mostly been focused on plotting the time domain response, the output waveform and the input waveform. We did a little bit of plotting with convolution too. So I guess you have convolution diagrams too. But this is a brand new type of plot for most of you. So this is called a pole zero diagram. And lost my pen. Sorry, I have to make a note. Some brand new type of diagram. And we're going to denote all the pole locations with an X and the zeros with an O. So X's and O's, just like the end of a letter or the song. So we are going to have every 0, which is at minus 3 and minus 7, denoted with an O. So at minus 3 and minus 7 in the complex plane. Remember, S is equal to sigma plus j omega. So this is saying this, x-axis is the same thing as the real part of S. The imaginary axis is the same as the real part, or the imaginary part of S. So this is just a complex plane plot. And so we had minus 3 and minus 7 as our zeros. Then we need to add a pole at negative 2, multiplicity 2. So what we're going to do is we're going to put negative 2, we're going to put an X. And then we're going to put a superscript 2 right by it so that we can say, hey, this is, multiplicity 2. So that little 2 floating there is just the multiplicity. And then we have poles at minus j6 down here and plus j6. Okay, so those each get an X. We expect them to be in complex conjugate pairs. So we expect this diagram to be symmetric about the real axis. And then at -4 plus J3 and S equals -4 minus J3, we have another X for this remaining set of poles that we identified right here. And for some reason, my plotter likes to make my X's look open. You don't have to draw them as open X's. You can draw them as closed X's. But yeah. What questions do we have? Homework 5 should already be posted in the assignment section. I will try to get it into the content section as well. Yes, very good for making the reference to the song. I'll fix that. I'll fix that soon. Homework 5 will be up soon. TM. Questions about pole zero plots or poles and zeros in general. So, sometimes it's very useful to plot out where poles and zeros are for reasons we will discuss shortly. So, relationship of poles to the natural response. So, I claim to you that the poles of H of S correspond to the natural response of the circuit, including indeterminate coefficients. Because, we can't determine the coefficients until we have a defined input and with initial values. So this could be seen clearly with an example. So with that same transfer function, we get that the impulse response. So we can break this up into its terms, and then we can do a partial fraction expansion where we'll figure out the coefficients above, s plus 2, s plus 2 squared, as, or, a3s plus a4 over s squared plus 36, and then, a5s plus a6 over whatever this factors back into. And we will get, using real valued functions. Remember, we like real value functions for real valued coefficients and inputs. So the natural response is just going to be b1 e to the minus 2t, b2 t e to the negative 2t, plus b3 cosine 6t, plus b4 sine of 6t, plus b5 e to the negative 4t times cosine of 3t, plus b6 e to the negative 4t sine of 3t u of t. So the poles are very important because, our natural response is set by them. So that's kind of connecting what we learned about transfer functions to what we already know about the natural response from the ODE lecture set into one thing. So the relationships of poles to stability. So poles will determine the stability of a system, an indication of whether the natural response will converge to a constant. So you want over time, the natural response converges to a constant value. So we focus on bounded input, bounded output stability, BIBO stability. So BIBO stability means that an input signal with an absolute value less than a constant bound produces an output signal that's less than another bound in absolute value for all time. So another way of saying this is, if your signal was f of t, you would have absolute value of f of t is less than or equal to b, where b is some constant, for all t. In other words, this is I don't want to say if it's equivalent, but like a consequence of this above is that an input signal of finite energy produces an output signal of finite energy, regardless of the specific form the signals take. Now, we haven't taken ECE 301 yet, where we talk about the energy in a signal, but you can conceptualize, if you take a signal and square it, that's some indication of whether it has, infinite energy if it blows up to infinity, or if it's finite energy, or you can square it and it'll still be okay. If you don't understand that, just stick to that middle sub bullet point where it talks about absolute value, and you should be fine. Most of the time, we're not actually concerned about finding the specific bound. We just want to know whether or not it meets this criterion called Bibo stability. So a system is guaranteed to be Bibo stable if all poles reside completely in the left half plane, LHB. So the real part of P sub L is equal to the sigma L less than 0. So for example, if we just had, the -4 plus or minus J3 and the -2 multiplicity 2 poles, if we just had them, all poles would be in the left half plane, and we'd say the transfer function is stable. However, any one pole in the right half plane, RHP, indicates that the system is Bibo unstable, with a natural response including exponential growth. So you can have a finite input, and your output will just grow to infinity. Not good. We don't want this in any sort of system that we deal with real things. If things are Bibo unstable, that's when your components usually break catastrophically, and they can never be used again. So if you've ever smoked a resistor in your lab, you know what this is like. So the real part of P is greater than sigma L, or the real part of P sub L is equal to sigma L, which has to be greater than 0. So we don't have any, but if you had any X's in our pole 0 diagram on the right half plane, so in quadrants 1 or quadrant 4, the system would be unstable, regardless of where the other poles are located. So what about if the poles are directly on the imaginary axis? So if you have a simple pole of multiplicity 1 on the imaginary axis, we call that marginally stable. So it's going to be a sinusoid if it's not at the origin, or it's going to be a step function if we have just one at the origin. And if it's not at the origin on the imaginary axis, you expect it to appear if it's complex conjugate. So like we had j equals -6, so we expect, or we had pole at minus J6, so we expect a pole at plus J6 as well, because we deal with real valued inputs, or real valued coefficients, so we expect everything, complex numbers must occur in complex conjugate pairs. We will define it marginal stability to be Bibo unstable for our purposes. So you can say, okay, overall, all of the pole 0 diagram for this transfer function tells us that this is Bibo unstable, if only these poles weren't located where they were. Then it could be Bibo stable. So why are we going to consider this to be Bibo unstable? So if you have a pole of multiplicity greater than 1, it's going to be inherently Bibo unstable. So you would have t times cosine of omega naught theta, or sine of t times omega, or t times sine of omega naught theta. So that would be the linearly growing sinusoid, which, as you can tell, if the sinusoid gets bigger and bigger in oscillation, that's unstable. And or it would be a ramp function if it was at the origin. So if you have a pole of multiplicity 2 at the origin, it'll have a ramp function where it's linearly growing without any oscillation. That's also going to be Bibo unstable because output grows for a finite input. So infinite signals will also result if the input matches the natural frequency of a simple pole on the imaginary axis. So if you apply a sinusoidal input with omega naught, or omega 1 equals to 6 radians per second, then this would also blow up, because you have applied a finite input, which is a constant amplitude sinusoid, but the output would blow up in the case where the frequencies match exactly. So this means that even the integrator, which is just h of s is 1 over s, is considered Beeble unstable because, this would become a step function. So even if you're just integrating a signal, it's Beeble unstable because you could integrate, a constant and get a ramp. No good. And what does the imaginary part of a pole tell us? So it helps determine the frequency of the oscillation involved. So what about the zeros? We've kind of ignored the zeros up until now. So the zeros do not affect the stability of an LTI system or natural response. So the zeros indicate what types of output will be missing from a forced response due to an input that matches the form of the zeros. So a little bit more concretely, so if you have a numerator factor of s plus a in h of s, then an input of k times e to the negative at u of t will not cause a term like a1 e to the negative at u of t to appear in the forced response. Because it's a zero, when you multiply the Laplace transform of our input by that, you would suddenly get a cancellation of this s plus a term with that in the denominator, so you don't get an output of that form. So it zeroes out certain inputs is what the zero does. Hence the name. So if you think about it, if your h of s is like an impedance, then h being equal to 0 means that you're getting a short circuit. If your h of y is of an admittance form, then your transfer function says where the zeros happen, you get an open circuit. And if you're talking about a voltage gain or a current gain for your transfer function, then you're getting absolutely zero transmission through a voltage or current between input and output at the zeros. What about the poles and zeros do you want me to explain further? Everyone good on this concept? Nice break from convolution. Nice break from having to visualize the complex plane. Frequency responses, definitely a little bit easier to grasp than I think, arbitrary input Laplace transforms, just because we're dealing with sinusoids now. And you can easily make a sinusoid and have it go on for all time. So it's not like you have to scope it to figure out what's going on like you would for the transients, to figure out, if the transient's even there. But here, we get, sinusoid, so you can just continuously monitor what's happening within the oscilloscope and a good signal generator. So in the lab, this is definitely for what we focus on. Hearing no more questions, I'm going to move on to talk about our second topic, which will be resonance in second order systems. So we got the math and the definitions of Beeble stability out of the way. Let's talk about resonance. So this is more of observations. So resonance is the phenomenon in which an input near the natural frequency of a system produces an output many times larger than the input. So if we talk about the circus tent analogy for poles and zeros, this would be a swing set analogy. So consider a very well lubricated swing set where the bearings are good and it's not rusty and old and all that. So if you have pushing someone on a swing set, you can just push and give a very light push and get them started. But if you time it just right, the time at which it takes for them to swing back, especially for low inputs, you can give a very light push, and then they will, the amplitude grows. And the amplitude grows, and the amplitude grows despite pushing very lightly, as long as you're not dissipating too much energy. you'll get that, oh, you can get, very, very large, amplitude swings on the swing set for very light pushes, which is good if you're an exhausted parent and you don't want to try too hard to play with your kids. I'm not a parent, just so you knows, but like when you're playing with energetic kids, it can definitely get exhausting to do anything more than stand in place and push. So resonance in circuits is associated with the interactions between inductors and capacitors. So in order to have resonance, you basically need at least one inductor and one capacitor for linear systems. Because you must be able to exchange electrical energy in the capacitor with magnetic energy in the inductor. You can't just exchange electrical energy for electrical energy or magnetic energy for magnetic energy. You have to be able to go in between the two. So specifically, electrical resonance occurs when the impedance emittance of some electrical components cancels the impedance emittance of another. So that's big. And you're like, how can we cancel impedance emittances? Like, if you think about a resistor, we don't have negative resistances in circuits, at least without dependent sources. So, but, we can have negative emittances when we deal with, the reactance and susceptance components. So the imaginary components can cancel each other out. So let's look at what this looks like. So let's look at this series LC circuit where we got this voltage source feeding L and C in series. So recall we have an undamped natural frequency omega naught, which is equal to the square root of 1 over LC, which is related to the natural response of the circuit. You'll have like some B times cosine of omega naught T plus phi, where B and phi are going to be undetermined coefficients. So rather than write it as cosine and sine components, I did it as, shifted, cosine or cosine with a phase, like we would for phasors. And phasors is kind of the way to go. So what we're going to do is write the transfer function. So in this case, we'll write IL of S over Vn of S. Well, since it's a series circuit, this is just going to be 1 over the total impedance. So 1 over Zn of S. It's 1 over SL plus 1 over SC. So we can simplify the transfer function. And we'll get H of S equals 1 over L times quantity S over S squared plus 1 over LC, where we divided through by L and multiplied by S, top and bottom. So we get 1 over L times S, and then we'll get S plus J over square root LC, quantity times S minus J times 1 over square root LC, close quantity. So, we just factored this, real quadratic term in the denominator into its complex conjugate poles. I guess just imaginary conjugate poles because they're purely imaginary. So poles are at plus or minus J omega naught, where omega naught again is 1 over square root LC, like we should be very comfortable with at this time. So we analyze the phasors. So we'll say S such that the real part is equal to 0 is the same thing as setting sigma to 0 and sigma plus J omega, which is J omega. So we'll get that Z of J omega is equal to J omega L minus J times 1 over omega C. So we just took this bottom part and we wrote it, replace S with J omega. And perhaps most importantly, you have to remember that 1 over J is the same thing as J to the minus 1, is the same thing as J cubed, or any, you can keep adding 4, subtracting 4 from it, which is equal to negative J. So recall that, 1 over J is the same thing as minus J. So hold on, now we went from addition to subtraction. This leads, this is promising for an ability to make this equal to 0. So if we investigate the natural frequency with these phasors, so we'll plug in J omega naught in place of where we had S before. So we'll get j omega naught L minus j times 1 over omega naught C. So this is j times L over square root LC minus j times square root of LC over C. Well, we can cancel square root of L from the numerator and denominator, leaving square root of L in the numerator here and square root of C in the denominator for our first term. And then we'll have subtracting off, well, we still got the j hanging out. We can cancel a square root of C from the numerator and the denominator, leaving just a square root of C in the denominator. Square root of L remains. So j times quantity square root LC minus square root LC, that's 0. So we get that z at the natural frequency is equal to 0, which, if we plug this into our transfer function, would say blows up to infinity. So, we would get infinite current for a finite input voltage. Uh-oh. Probably don't want that. So the impedances of the inductor and capacitor cancel out to 0 at natural frequency, leading to that infinite current output for a finite voltage amplitude input. So we call the natural frequency a resonance frequency in this case, omega r, where r stands for resonance, equals omega naught, the natural frequency. How are we following? So hopefully we see that the natural frequency that we defined before now takes on new significance. So what do you think is going to happen if we add resistance? Anyone want to venture a guess? Or look ahead and tell me what I'm going to say? Damping. Good. Good guess. Good guess. We will get damped outputs. Let's see what that looks like in an example. So now we're going to evolve from the series LC circuit to a series RLC circuit, where we're taking the voltage across the capacitor as one idea, and then we'll take the inductor current as another idea. Inductor current being the current shared by all elements of the circuit. So we'll write the transfer function, IL of S over Vn of S. So IL will be our output. So we'll get 1 over Zn of S again. So we just look at the equivalent impedance in the S domain, which is equal to RS plus SLS plus 1 over C, or 1 over SCS, where the subscript S in after every component value just reminds us that it's in series. Because we'll have to keep track of what's going on in more complicated circuits soon enough. So we'll analyze the phasors. S at sigma equals 0 is equal to j omega, as we said before. So we could just say Zn of j omega is equal to Rs plus j quantity omega Ls minus 1 over omega Cs closed quantity. So we'll investigate the natural frequency with phasors. So we plug in omega naught. We'll get Rs plus j times quantity omega naught Ls minus 1 over omega naught Cs, where we figured out exactly what's going to happen before. So we know that this imaginary term will go to 0. So we'll get Rs plus j 0. So at the natural frequency, the natural frequency is the resonance frequency again. So omega r is equal to omega naught. at which the series, inductor, and capacitor behave as a short circuit. So we don't get an elimination of all the things in here. We will get that there is a finite output for a finite input. So it will be nice and stable, but that's just due to the presence of the resistance here. Because if we apply an input, we just divide by RS, and that'll be our current output. But we no longer have a voltage drop across the L and C in series. Or the other way of saying that is the voltage drop across the L will equal the voltage drop, phasor voltage drop across the capacitor, equal and opposite. So what happens in a parallel RLC circuit? So with phasors, Yin is going to be equal to 1 over R sub P plus J times quantity omega times C sub P plus 1 over omega L sub P, where we have used the subscript P to denote parallel. And remember, the admittance of a capacitor is just S times C sub P, whereas the admittance of an inductor will be 1 over S L sub P, where when we plug in J, remember we have 1 over J omega L. Wait a minute. That's a mistake. That plus sign in the parentheses on slide 15 should be a minus sign, because 1 over J is equal to J cubed is equal to minus J. So that's a mistake. Sorry. So investigate the natural frequency of phasors. So we get that Zn, J omega, is going to be 1 over Rp plus J0. So just 1 over Rp. Wait, that's not right. That should be Y. Yeah, it shouldn't be Zn. That should be Yn. So the natural frequency is the resonance frequency again, omega R is equal to omega naught, at which the parallel inductor and capacitor behave as an open circuit. And perhaps also importantly, some of you get tripped up with this, anything in parallel with an open circuit is equal to the other thing. So RP in parallel with the LP and CP at the resonance frequency is RP in parallel with an open circuit. So we're just left with the effect of RP. So in general, circuits that do not have RLC all in series or all in parallel will have omega R not equal to omega naught, especially when multiple resistances are involved. And we will do that example next time. But before I let you go, I do want to figure out what questions we have. No questions? All right. Have a good day. I will be going to my office for office hours, grabbing lunch along the way like I normally do. Bye, everyone. So long.